Welcome to the Australian Water School, the home of demand-driven industry-designed training for the global water sector.
I'm delighted once again to welcome you to this webinar presented by the Australian Water School. So good to see so many here today. We'll be talking about lake modelling and the complexities of modelling stationary water. This is going to be a good time, and I'm so glad so many have joined up. Presented by Michael Barry, panellists Louise Bruce, Emma McCall. My name's Trevor Pillar, and I'll be chairing today. How is this on the map coming up now? Look at that. That is a good spread. All over the world, at least 70 countries, plus 70 countries and more have joined us today. Thanks so much. Right, let's get on to this. This is great. Hi, Michael. Hi, Emma. Hi, Louise. It's so good to see you guys. I haven't got a clue where you're from, but I think it's eastern states of Australia. Is that right, Michael?
Emma and myself are from Brisbane, yes, and Louise is in Perth. That's right, on the West Coast. Yep.
Nice to have you. Emma's from Perth.
No,
Right.
Louise is in Perth.
Louise from Perth,
Yep.
Got it. Okay, no wonder it's looking harder. No, it's not. You're all very, very clear. 2,000 miles away, how far? 2,000 kilometres away. That's great. And I'm in South Australia, the central state in Australia, the one that really counts. No, don't worry.
Yep.
We'll get into state politics if we go there. Happy to be here today, you guys. I can see that. Michael's going to present. Louise and Emma, you're going to be tickling the ivories. What a way to say it. This is not true. Any questions or comments you have, Louise and Emma will be firing away while Michael's speaking. So do please shoot them. What do you think? The hardest questions, Louise? Your mic's not on.
Yep, please. The harder the better. We're
Right.
ready.
Okay. Right. So you got your fingertips at the ready, Emma. All good.
We're all ready to go, but we are going to save the hardest questions for Michael at the end.
Oh, right. Yeah, that's right. That's right. Give him a hit before he starts. That's good. Puts him on his toes. It's great. All right, we are underway, and we can't wait. Thanks a lot, Michael. We'll hand right over to you.
No problems. Thanks, Trevor. Okay. Thank you very much, Trevor and the Australian Water School for hosting us. It's very much appreciated. What we're going to do today, as Trevor mentioned, is we're going to talk about modelling of lakes, and particularly stationary water quality modelling. And it sounds a bit easier than modelling very fast flows, but we'll talk about a few of the complexities, perhaps, that confront modelling of these more quiescent systems. In terms of today, we'll talk a little bit about the key processes in the systems that we're considering and what those systems are. And we'll look at a numerical model that we have built of a typical system. It's just a demonstration model. It's not a real system, but we'll look at that model and we'll interrogate that model, and we'll look at its predictions in relation to the sorts of issues that we come up with typically in these sorts of systems. Particularly, we'll look at three traps that can be fallen into quite easily in modelling these systems, and how to avoid those traps, and to at least, or perhaps know they're there, and minimise their impact on our modelling predictions and outcomes. And then we'll look at an example. It is a real world example that we'll look at, and hopefully we will be able to tie it all together in that example in terms of what we're chatting about today. So we'll start with the key processes. But we'll start with what we're actually talking about. And so what is a typical lake or reservoir? What does that mean? Well, we think of these systems as deep lakes. Tens of metres is a typical sort of depth. They can go up to 100 metres or more in some cases. Most importantly, though, they're inland with no tides and they're freshwater. So we're talking about deep freshwater inland systems. These systems receive inflows from upstream. They might be catchment-derived inflows, and they also can deliver water downstream. And we've got a picture there of one way in which water can be delivered downstream from what looks like a water supply reservoir, but it could also be natural stream delivery, or it could be a piped offtake in some cases, or weirs, or a combination of all these things. So more or less, we're looking at deep systems that are fresh, that don't have tidal forcing, and interact with their environment through receipt of upstream water and delivery of water downstream. Now, what I'd like to do to talk about these systems to start with, I'd like to talk about the water movement characteristics of these systems. Then we'll talk about water quality characteristics of these systems. And then we'll talk about those in combination and how those two things work together to give us some features, some ecological and environmental features of these systems that are important when we come to model them. Now, I will say that this area of research and modelling is many, many, many decades old, and there's fantastic research being done all around the world in this space. This 1 hour session is by no means a complete overview of all that research that's ever been done. It's very much today going to be a high level description of what I think are the key processes in these systems. So we don't have time to go through all those processes, but I will certainly touch on what I think is the most important, certainly in terms of what we need to have our minds around for subsequent water quality modelling of these systems. So if I've omitted something, please forgive me, but it's most likely in the interests of time brevity. So we're going to talk about water movement first in these systems, but before we do that, we're going to kick off with a comparison of other environmental systems that we often encounter in the modelling world. So what we'll do is we'll kick off with a bit of a comparison of the features of floods compared to the features of lakes and reservoirs. And hopefully we'll be able to start that mindset of moving away from thinking about modelling as other systems that we've talked about and towards what the modelling requirements are for lakes and reservoirs. In terms of floods versus lakes and reservoirs, floods are very much interested in the lateral directions of flow. So the X and Y, they matter most in floods and flood models. But in lakes and reservoirs, actually, it's the vertical direction that matters. X and Y is important. There are some lateral variations and gradients in lakes and reservoirs, but much more important, as we'll see today, is the vertical or the Z direction. I haven't seen too many flood models over the years that are three-dimensional. It's usually two-dimensional, and that's because that third dimension, the vertical, is not really of interest in flood modelling. In floods, we're really interested, obviously, in velocities, and there are significant mean flows, as we can see in the picture on the right there. Significant mean flows in floods, and we need to capture those in our models. In lakes and reservoirs, yeah, not really. Those mean flows are near zero, not always zero, but near zero most of the time. And instead of mean velocities being of most importance, actually turbulence and mixing processes are more important typically than mean flows, which is quite contrasting to what we've come across in floods before. Flooding and flood modelling is typically associated with short-term behaviour and impacts. That's weather. So an event or perhaps a couple of events that come through in a series of days or perhaps a week. That's what we concern ourselves in flood modelling. In lakes and reservoirs, we're interested in longer-term behaviour and impacts, which is climate. So seasonal, interseasonal and interannual climate is what we're really interested in lakes and reservoirs rather than short-term behaviour. And we'll get to this in a minute, but water temperature, simulating water temperature in flood models, I don't think I've seen that too much in the past, but water temperature is everything to lakes and reservoirs. And if we don't simulate water temperature, and if we don't have that simulated correctly in our lake or reservoir model, we don't have any hope in getting the hydrodynamics right. So I'm hoping that we can realise that modelling lakes and reservoirs is really quite a different proposition to modelling something like floods, or even understanding the ecological and environmental processes. It's a very different matter. And some of those aspects of those differences I'd like to talk about today, and again, get back to those traps of what we might fall into in terms of modelling of these quite different systems. Water movement, what matters most to a typical lake or reservoir? We've talked about a couple just now, but I will say hands down, in my view, the most important thing in terms of water movement in a reservoir is climate. And we're talking about the different aspects of climate, which I've listed there. Why are these the most important? Because the climate conditions in which a lake or reservoir finds itself determine water temperature. And this is really important because if we're modelling lakes and reservoirs, we have to get temperature right. And these are the things that determine or dictate that temperature as the hydrodynamics in a lake or reservoir unfold. Also of importance are turbulence, gravity, and depth. And turbulence gives us mixing, and gravity, we'll talk about in a minute, but gravity essentially means that we have warmer water floating on top of colder water because warm air rises, warm water rises as well. And so turbulence, gravity, and climate together give us the governing hydrodynamics of lakes and reservoirs. So climate gives us water temperature, turbulence and gravity and the depth of the reservoir, they give us the vertical distribution of that water temperature, and they combine to provide or determine the governing hydrodynamics of the system. So this is why these are the key things that we'll talk about over and over again today. And I guess there are other processes as well, one of which is inflows, and inflows can have an impact on reservoirs, but today we'll be concerning ourselves primarily with the operational modes of reservoirs and lakes, so without considering the impacts of inflows. So water temperature is everything, turbulence and gravity and depth, determine the distribution of that temperatures in their reservoirs, which provide the governing hydrodynamics, which we have to make sure we get right in our models. So let's look at that. Let's look at that visually or pictorially. In terms of water movement, what we've got here is just a conceptual column of water in a reservoir. So this is the bed of the reservoir, and this is the surface of the reservoir. And it's obviously not in the shape of a reservoir or lake, but it's just a conceptual model to try and discuss a few ideas about how these hydrodynamics work. So this is the water column, this is the bed, this is the surface. And in wintertime, we have some heating from the atmosphere. We talked about climate being important. Well, this is why. So we have some heating of the surface and some wind blowing on the surface. And we have turbulent mixing going from the top of the reservoir or lake down to the bottom. So what happens in winter is that there is some heating, but the wind typically applied to these reservoirs can overcome any sort of heating gradients and mix that warmer water downwards all the way to the bottom of the lake. And that mixing occurs through turbulent processes. So in winter, we don't have very noticeable at all temperature gradients in our lakes or reservoirs typically. However, when we move to summertime, it's a different story. And in summertime, the heating applied from the climate to our reservoirs increases substantially. And what happens then is that surface waters that receive that climatological forcing, they warm up considerably. And the wind may or may not be able to overcome that warming by mixing vertically, and typically it can't. So what we see in summertime is instead of mild heating at the surface and good mixing to the bottom, we see strong heating at the surface and poor mixing downwards. And what that means is that the surface waters are warmer than the bottom waters. And because of gravity, surface waters that are warmer, they float upwards, and waters that are colder, they stay in the bottom. And what that means is that while the surface layer that's warmer might be well mixed in itself, it cannot communicate very well at all with the bottom layers. And so the bottom layers become isolated from the top layers, and there's effective barrier between the two, because the wind mixing, the wind generated mixing, cannot mix that temperature downwards like it could in wintertime. In summertime, it can't do that. So what matters? Climate matters, as we talked about, because it's a source of heating and a source of stirring from the wind. Turbulence matters because it generates mixing and it can overcome temperature gradients. And gravity matters because warm water floats on top of cold water. And therefore, the most important direction that we concern ourselves, typically with reservoirs and reservoir modelling, is the vertical, which again is in quite contrasting to flood modelling. So climate, turbulence, gravity, and the vertical direction is what we're concerned with in terms of hydrodynamics. The word that we give to this separation of temperatures is thermal stratification. And you'll hear me say that over and over and over and over again today, because that's what the majority of this webinar is about. It's about thermal stratification, predicting that stratification, and looking at the water quality impacts of that stratification in reservoirs, in measurements, but also in simulating those processes. So between climate, turbulence, gravity in the vertical direction, we end up with thermal stratification in summertime, and this can cause water quality problems that we'll look at in a minute. So we've talked about water movement in reservoirs, and I've talked about the vertical direction being the most important, and climate being a driver there for those gradients to develop in temperature. In terms of water quality, what matters most to a typical lake or reservoir? Well, in my view, in terms of water quality, the most important water quality constituent or parameter is dissolved oxygen. Dissolved oxygen supports life. Not all life, but the majority of life is supported by oxygen. And the golden rule in terms of oxygen in natural environments is that high dissolved oxygen concentrations usually means good water quality, and low oxygen concentrations usually means poor water quality. So we do strive to maintain high oxygen concentrations in our reservoirs and lakes as best we can to avoid poor water quality developing. Now, where does oxygen come from? It comes from the surface. It comes from wind mixing and stirring. And what happens is the wind ruffles the surface of the lakes or reservoirs, and oxygen gets diffused and mixed down through the system through that process. Oxygen is also consumed at the bottom of lakes and reservoirs, at the bed, I'm calling it, and the bed is a sink of oxygen. And that oxygen is consumed at the bed because biological activity consumes organic matter as a natural environmental process in the sediments, and that consumption of organic matter also consumes oxygen. So that's why oxygen disappears into the sediments, but it's replenished from the fluxes or the mixing from the surface. After dissolved oxygen, I think probably the next most important thing, certainly in terms of what we're talking about today, are bioavailable nutrients. And we're talking about nitrogen and phosphorus here. And the golden rule for bioavailable nutrients in these sorts of systems is that low nutrient concentrations are generally good and high nutrient concentrations are generally bad. And we'll talk a bit more about why that's the case in a minute. But the complication or the little feedback loop we need to think about here is that low oxygen concentrations do often lead to high nutrient concentration environments being developed. So low oxygen in itself is a poor water quality outcome. It can generate a secondary poor water quality outcome, which is high nutrient concentrations, and that happens in the bed because nutrients are more often than not released from the bed as part of that organic matter breakdown process. Yes, there are nutrients that come from inflows as well, but we concern ourselves today with just these processes. Nutrients really do come from the bed as part of that organic matter breakdown. When the organic matter breakdown occurs, oxygen is consumed and nutrients are produced. And those nutrients are bioavailable. And what that means is that they are in a form that can be eaten up as food by things like phytoplankton, which is our third constituent here, which I think is very important for reservoirs, is phytoplankton, sometimes called algae. And algae and phytoplankton, they live more or less in the surface more often than not of reservoirs because those waters are sometimes, well, usually warmer, and there's light in the upper layers of reservoirs, and phytoplankton are small plants and they need light to grow and to survive. So they typically live in the surface layers. So when those nutrients get released from the bed and communicate with the surface layers, phytoplankton will often take up the nutrients as food and say, thank you very much, we're going to grow now, and sometimes bloom. So that blooming is bad. So the golden rule for phytoplankton is that low concentrations are good and high concentrations can lead to poor water quality. There might be some instances that we've heard of before where some types of phytoplankton can potentially be toxic. And so when they bloom in a reservoir or a lake, they release toxins that can cause humans rashes and can kill some sorts of biota. So we really do want to try and keep phytoplankton concentrations down. So what have we learned from this across these three constituents, water quality constituents? We've really learned that there are two key locations in reservoirs that things happen, and that's in the surface where dissolved oxygen is delivered to the water column and where phytoplankton grow, and at the bed where dissolved oxygen can be consumed, nutrients can be released, and in general, water quality can be poorer. So once again, we're talking about this vertical dimension. It's really about the transfers and communication between the top of a reservoir water column and the bottom. And that's what really matters in reservoirs. Lateral dimensions a little bit, but vertical dimensions are everything for both hydrodynamics and water quality for the reasons we've just talked about. So let's look at the key locations in terms of water quality, the surface and the bed, as we talked about. Here's our same water column that we looked at before. Again, it's a reservoir with the bed down here and the surface up here. And we have wind generating mixing and entraining oxygen that then gets mixed all the way down to the bottom, where oxygen, as we said, is consumed in the beds and disappears. So as long as this consumption of oxygen in the bed can be replenished by the entrainment or introduction of oxygen from the surface, we'll remain at fairly high dissolved oxygen concentrations in the water column. Why? Because we have turbulent mixing again playing a role in that transfer of oxygen from the surface to the bottom. In terms of nutrients and phytoplankton, here's our same water column, but now we have nutrients entering the system from the bottom, and that's where the organic matter consumption or degradation is occurring, and nutrients are being released as part of that. In this case, turbulent mixing moves those nutrients upwards through the water column to the surface. And that's why reasonably uniform concentrations of nutrients throughout the water column in these sorts of conditions. Phytoplankton will typically, however, live in the surface, and that's for reasons around light. They need to have light to grow. Now, phytoplankton, it's not a bad thing in itself. They're a naturally occurring organism, and they're all through very well and healthy ecosystems. It's when they bloom and become at very, very high concentrations and potentially toxic that problems can occur. So what matters again from water quality? We talk about what matters from water movement. What matters from water quality is oxygen. It supports life. Nutrients, they're food. And phytoplankton, if they get out of control, they can be problematic in these sorts of systems. Now let's bring that together and let's look at the winter scenario. So let's go back to thinking about our temperature gradients in winter, or lack thereof. Remember that we have not very strong heating from our climate and probably strongish wind in winter. We have a nice, well-mixed water column. If we add to that water column our oxygen dynamics that we just looked at, which is entrainment from the surface and consumption in the bottom, and our nutrient dynamics, which is release from the bottom and phytoplankton consumption in the surface. If we add a well-mixed hydrodynamic system to these processes, what do we get? Well, we get a water column that's pretty well mixed in terms of oxygen. We've got high oxygen throughout. We've got low nutrients because they're being nicely mixed, and phytoplankton aren't blooming because the nutrient concentrations are low. They're not being released excessively from the sediments. So in wintertime, when we don't have that really intense radiation from the sun, we usually have reasonably good quality in our reservoirs and lakes because we don't have that thermal stratification. Tick. In summertime, however, as we talked about, this heating increases greatly in terms of the surface layers. We have warm water on top and cold water on the bottom with a barrier between the two. If we add our oxygen and phytoplankton process to that, like we did before, what we get is low dissolved oxygen in the bottom layers and high nutrient concentrations in the bottom layers and potentially high phytoplankton concentrations in the top layer. And this is bad. This is something we want to avoid because we know that phytoplankton blooms can be problematic and high nutrient concentrations can also be problematic. So this is how we're bringing hydrodynamics together and with water quality to try and understand the key processes that we must capture in our models when we build them of these systems. So in terms of water movement and quality, what matters most to a typical lake or reservoir model? I'll say it over and over again, reproducing thermal stratification over seasons is absolutely critical. If we don't do that, then we will not be understanding or capturing the dynamics of our systems appropriately, and we'll get incorrect answers. And we'll talk about that in a minute. We must calibrate against measurements. It's non-negotiable. We must be looking at how our model performs in terms of temperature with depth, oxygen with depth, nutrients with depth, and phytoplankton as well. Inflows are important, and we'll look at those some of those later on, but for the purposes of calibrating an operational mode or reservoir in operational mode, these are the most important things we have to pay attention to, because if we don't, we'll get things wrong. Why would we build a model of a reservoir anyway? What sort of real world problems are we looking at? Well, we want to understand and manage phytoplankton blooms, and we've talked about why that could be the case in terms of toxins. We'd like to manage potable water offtakes. So we don't want to be drawing water from the reservoir for potable supply that is of poor water quality. That would be potentially what costs us a lot more money at our water treatment plant to process that water, and there's potential risks downstream to our consumers. So we want to avoid doing that. We might use our model to help us design artificial mixing devices, and we'll look at one of those a bit later on. Certainly in terms of informing catchment management, and where to spend money in catchment remediation to improve water quality in reservoirs, important use of a model, and that means meeting water quality objectives. So all these things about environmental management and quality of supply for potable sources is why we would build a model of these systems. Okay, so let's look at a numerical model. Always beware that we don't just build a model because it's fun or build a model to answer every question to every person. Quite the reverse. We have to always think of the questions that we're trying to address when we build a model, so we can build a model to address those questions, because a model cannot be everything to everybody or every process. So the two typical questions that come up in this space of reservoir and lake modeling are, how can offtake locations be managed to avoid drawing poor water, as we just talked about? And are there likely toxic phytoplankton dynamics going to be occurring in my reservoir? Or if they are, and I've seen them, observed them, what can I do about them? These questions are fundamentally both related to thermal stratification again. So here we are again talking about thermal stratification because this is what drives these sorts of questions to be asked. So we must make sure our models can capture these thermal stratification processes. And that's what we're focusing on today through our demonstration model. Okay, so we have built a demonstration model. This is the bathymetry spinning around on the right-hand side. It's obviously idealized. It's a bowl model. We've used TUFLOW FE and the TUFLOW water quality module to build this model and run some simulations, which we'll look at very shortly, the results of. It is three-dimensional. It's fully three-dimensional model. And the bathymetry you can see on the right-hand side there, it's about 20 meters deep. So blue's at about minus 20 meters and red's at about 0. At the lips, the top surface lips of this bowl, they're about 7 kilometers by 4 kilometers. There's around about 400 two-dimensional cells and about 4,000 three-dimensional cells. We've used a hybrid fixed and sigma layer vertical discretization in our model, and we'll talk about that in just a second, to have about 16 vertical layers. So just to reiterate, it's a three-dimensional model, and we've used TUFLOW FE and the water quality module to simulate likely dynamics in this system. Now, in terms of the vertical layering, this is important because we'll talk about it a little bit later on. It's broken up into a hybrid system, so we have fixed vertical layers from the bottom up to a certain height, which means these cross-sectional lines here don't move up and down. And on top of those, we have 4 sigma layers, and these layers do move up and down as the water level changes. And what you should be able to see is that there's a horizontal disconnect between some of these cells in the sigma layers that is not present in the vertical fixed Z layers. And we'll talk about some of the impacts of that later on. But that's a discretization we have used in our model. The climate we've applied, because climate's important, we talked about that, is a typical subtropical Australian climate, and we've executed the model from more or less winter to the following autumn, so over a complete summer cycle. We talked about climate being important. We talked about mixing and turbulent mixing being important. So the turbulent closure scheme that we've used as our base case model is a second order K epsilon model. But what is a turbulence closure model? I'm going to spend 1 minute talking about this because it's important, because it's one of the key processes that dominates reservoir dynamics. In hydrodynamic models, we typically cannot resolve turbulent scale processes, which might be in the order of millimeters to centimeters. So we can resolve processes that are on the scale of meters, which are the same size or comparable size to our computational cells. So if our computational cell was, say, 2 meters magnitude in terms of its size, turbulence is 2 centimeters, we can't resolve turbulent processes, but we need to include them in our model because we know they're important because they generate mixing and that changes temperature gradients. So a turbulence closure scheme is more or less a way of relating bulk or larger scale processes to small scale processes. We simulate the large scale processes, we don't simulate the small scale processes, so we need a model that links the two together so that from large scale process simulation, we can infer what's happening at those smaller scales, i.e. turbulent mixing. There's so many different turbulent closure schemes out there that do this for us. And so what we'll do with this model is we'll look at to see the impact of changing those turbulence closure schemes on the predictions of stratification. So the one we've used for our base case is pretty widely used. It's a second order K epsilon model. It relates large scale processes to small scale processes and allows us to capture or at least parameterize turbulent mixing. What did we simulate in the model? We simulated, in terms of water movement, we simulated water level with evaporation, velocity, temperature, and density. In terms of water quality, with the water quality module, we simulated dissolved oxygen, silicate, nutrients through ammonium, nitrate, and phosphorus, and 1 phytoplankton group, in the hope that we'll be able to resolve these sorts of processes that we've been talking about so far. Now, in terms of the presentation of results, I'll reiterate it is a three-dimensional model, but I'll be presenting only information from a profile right through the middle of the lake, just with this arrows going up and down. And you can think of the way I present that is I look at different profiles evolving in time, and I stack these profiles together one after the other in time to come up eventually with a color contour map like this that has depth always on the vertical axis and time always on the horizontal axis from winter, spring, summer through to autumn. So it's a 3D model, but I'm presenting a one-dimensional view of that model, which is a vertical profile in the middle of the lake. Color contours are always given by the color bar and the title. So this is temperature contours from 10 degrees is blue to 25 is yellow. And similarly for dissolved oxygen from 0 to 8 milligrams a litre is blue to yellow. And if I want to draw your attention to something, I'll put a red box around it. So we have a base case model that uses Australian typical subtropical climate, a K epsilon closure scheme, and is about 20 metres deep. These are the base case results, and I'll be showing these results over and over again as comparison points for what changes in the model, the sensitivities of the model. So I'll talk very briefly through these. We have temperature, dissolved oxygen, ammonium, and phytoplankton contours, and these will always appear in this order. We're starting in winter, remember, we're going through summer, and we are finishing up in autumn. And again, this is obviously a Southern Hemisphere model because we have warmer waters during December, January. It's in the Southern Hemisphere. The reverse is true for Northern Hemisphere. Importantly, in wintertime, as we talked about earlier on, the temperature is well mixed throughout the whole depth of the water column. That's why we're blue from top to bottom. In summertime, we're yellow on the top and greenish on the bottom. And that means we have a strong thermal stratification between the top and the bottom. And this is being predicted from our model with those assumptions we talked about for the climate and the turbulence closure scheme is predicting this thermal stratification, which is good because that's expected behaviour. Also expected behaviour is underneath this stratification, this thermal stratification, is low dissolved oxygen, which is the blue areas here. And they're almost down to 0 milligrams per litre. That's as expected, as we talked about before. Stratification gives us low dissolved oxygen, which gives us nutrient release. This is ammonium contours, which are representative nutrients. We can see high concentrations of ammonia here and high concentrations of phytoplankton that have eaten some of this ammonia to grow. So it's the classic process we've talked about, which is thermal stratification to dissolved oxygen stratification to nutrient release at the bed to phytoplankton growth on the surface. And that's really what we're talking about in these comparisons. And again, I'll draw your attention to particular areas on this plot with these sorts of circles and boxes. So 3 traps to match up with what we think about is important, which is climate, turbulence, oxygen, nutrients, and phytoplankton on the left-hand side. Trap 1 will look at climate. Trap 2 will look at turbulence closure scheme, and trap 3 will look at our vertical solution scheme, which is the sigma layer, fixed layer thing we talked about before. Why? Because all these things are related to thermal stratification. Again, in the vertical, we're talking about thermal stratification. So all these things can influence that and therefore our predictive capability. Okay, climate data. We can get climate data from lots of different areas and locations. On-lake data is often the best. And these are stations that are mounted on the lake. They float on the lake and they collect all sorts of meteorological data. They can be great, but they could also be placed in places that are not appropriate, or they might not be maintained appropriately or recalibrated appropriately. So we still need to understand the quality of our data in these systems, even though we might have data collected right from on top of our lake. So what we're going to do in this example is understand some of the impacts of not paying attention closely to our forcing data from the climate, because we know climate's important. And we're going to look at changing the wind field applied to this model and seeing what happens. First, we're going to look at completely missing one wind event that went across the lake in this example. Perhaps our weather station got knocked out by the wind event and we didn't replace it properly. And then we're going to look at an example where instead of using 6-hourly data for our wind field, we're going to use daily data. And we're going to see what impact that has on the thermal stratification of the lake, predicted thermal stratification, because that's what we know matters most. So I'll run through a series of results here, and in all cases, they're the same, presented the same. These are the same panels we talked about before, and I've just added a wind time series on the top. Now, at the moment, I have this rectangle area reproduced over here as the baseline information. So at the moment, this is the same as this panel. But as I go forwards, this panel will change depending on what scenario I've simulated in the model, but this panel will stay the same. So you'll be able to compare what's happened over here to what our base case was here. So in this case, I'd like you to look at these particular areas which I've got circled as I move through. And what we're going to do is we're going to pretend that our weather station missed this mixing event here, this high wind speed. We're going to pretend it missed that, And we're going to look at these two areas in this panel, which will change as I go to the next slide. But these positions, these two areas will not change on this side. So what happens when we miss that wind event? It's disappeared from our record. We can see straight away that we've got a very different prediction for temperature and dissolved oxygen in these locations here. And in fact, we have dissolved oxygen concentrations that are low at the bottom of the reservoir for an extended period. And even because we missed that 1 or 2 day wind event, it means we have a very different profile of concentration at depth for weeks or months afterwards compared to the base case over here. Much, much lower dissolved oxygen concentrations here compared to here. So missing a single event in terms of our climate forcing can really influence our reservoir predictions. Similarly, we have much higher nutrient concentrations at the bed related to this low dissolved oxygen, and we have higher phytoplankton concentrations, which we'll get to in a minute. So just by missing one event, we've completely changed our model predictions. And that's really something we need to grapple with when we're doing this modeling, because these errors or these emissions are cumulative. They don't get washed out with the tide or a big boundary condition. They stay there. If we make a mistake, they stay there. Now what we're going to do is we're going to say, well, let's not apply 6-hourly wind data. Let's apply daily wind data instead. So this is the baseline again. This panel is going to change when we change our record to daily. So we see a much lower frequency of reporting of the daily measurements. And look what we see. We see massive reductions in dissolved oxygen at depth, huge release of nutrients at the bottom. And this is off scale, actually. It was too high. The concentrations were too high to report. And they're vastly, vastly different to what we had in our base case. And look at the phytoplankton concentration in the surface. They're much greater than they were in the base case. And that's just from using a daily record instead of 6-hourly for our weather data. So that was climate. Trap number 1, climate. Be very, very careful about what weather data you apply, because it will greatly influence stratification and water quality. Trap 2 is about turbulence closure schemes. As I said, there's many available. We've used second order K epsilon in our model to start with as a base case. We're going to look at 3 others: length scale method 1, I'm calling them, length scale method 2, and a constant diffusivity. They're just different ways of estimating turbulent properties at the small scale from large properties at the large scale, which we do simulate. And look, this is an ongoing concern of modelers, and this is an example of a publication where people think about these sorts of things. It's not just something I've made up. It's something real we need to make sure we're across in terms of our modelling of these reservoirs. So here's the baseline again. You've seen these results before. There's nothing new here, but do pay attention to where these circles are. If I go from the K epsilon model now to the length scale 1 model, we see more mixing at depth. Dissolved oxygen is being mixed down further. Nutrients are sort of a bit high in phytoplankton, perhaps. But if we go to mixing a length scale method 2, we see very, very different results with depth. And in fact, we see dissolved oxygen is no longer stratified in the vertical, and neither are nutrients, and phytoplankton concentrations are just about disappeared. And that's just because we chose a different closure scheme for our turbulence model. That's all we did. That's the only difference between the simulations. And of course, if we go to a constant diffusivity, we see there's no longer a temperature, a thermal stratification predicted. There's no longer a dissolved oxygen gradient predicted, and there's almost no nutrient release, and the concentrations of phytoplankton are very low, which we think it's wrong. It's not going to be right. So the takeaway message is, just by changing our turbulence closure scheme, we get very different results. We need to be very, very cautious as reservoir modelers about these sorts of things. Trap number 3 is the vertical solution scheme. There's 2 primary schemes that are used. I know there's more, but the 2 that are mainly used are the hybrid, which is our base case here, which is our fixed layer with some sigma layers sitting on top. And the second is all sigmas. And all sigmas means that we have the same number of layers at every depth in the model. So in this case, we have 20 layers, 20 layers in the shallows and 20 layers in the depths, in the deep parts, which means sigma layers are contour or bathymetry following. And what that means is we can get horizontal disconnects between computational cells, and that has implications for simulating stratification. So let's look at those results. Again, this is baseline. You've seen this before with our thermal stratification and low dissolved oxygen. This is for the fixed Z with the sigma layers on top, our baseline model. If we do nothing else other than move to a sigma layer model, this is what we see on the right-hand side in terms of stratification. we get much more mixing of temperature to depth. We get very different dissolved oxygen predictions, lower nutrient concentrations, and lower phytoplankton concentrations. Why? Because we just changed the vertical layering scheme. Now, the reason for that is that the artificial gradients in density can develop between these cells that are not perfectly aligned horizontally. So generally, we wouldn't use sigma layers to try and resolve these stratification processes if we really wanted to get them right, because we know that that's a numerical process that happens in all numerical models. It's not just specific to one or two. It's a solution scheme thing. Okay, so the three traps are, it's all about thermal stratification. Everything in these reservoirs and lakes is all about thermal stratification. Lessons we've learnt: climate simulation, climate forcing is absolutely critical. If we get that wrong, we're not going to get our model right. Turbulence is critical, not mean flows, not so much, but turbulence is critical, and the mixing schemes we choose can be very important. Solution schemes matter, and calibration is non-optional. We should absolutely not be preparing these models without calibration data. However, be not afraid. With the right information and expertise, this can definitely be done, but there are traps along the way that we could fall into unknowingly if we don't quite do the right thing at every stage. And we've got a long track record of doing that with TUFLOW FV. So what we'll do is we'll finish up with just a couple more minutes on an example. And this is a real world example of, not what I'm showing you here in the animation, but it's a real world example of somewhere else where we've used TUFLOW FV with the water quality module that goes with TUFLOW FV to simulate an inflow into a reservoir. So a catchment inflow from upstream into a reservoir. What we've done is we've looked at three different situations where, because of potentially different assumptions we've made with our climate or our mixing or our discretization in our model, we've come up with different vertical stratifications in the receiving reservoir for three different instances. So we're looking at the same inflow, but three different receiving environments, and they're different only in their vertical thermal stratification state when that inflow arrives. The question we're asking is, well, when the inflow comes in, where should we have our offtake vertically? Where should it be to avoid the inflow? Because often inflows from catchments are poor water quality. So where should we place it? So this model is about looking at what happens in an inflow and how that inflow insertion location in the reservoir changes with different ambient thermal stratification conditions. So what we'll do is we'll move to the next slide, which has three examples here. So we have, again, the same inflow coming into the reservoir. This is a view of a reservoir in perspective. So we're looking into the distance as we go back. Here's the inflow. It'll come in through the reservoir this way. There's a cross-section, also a cross-section through the vertical in the reservoir, which is section A, which is across here. We have three different conditions of background stratification in these instances. So here we have conditions that such that the same inflow will be an underflow. Here we have conditions such the inflow will be a intermediate flow or interflow, and here the conditions will be such that the inflow is a surface flow. And that's only because the stratification in these different examples when the inflow arrives is different. So let's have a look at this animation. Looks like there's an issue with the animation. I apologize. I'm sorry, there is an issue with the animation. However, what we would see is that in this case, an underflow would come in and would come up to about here on the offtake. The interflow would come in the middle and the surface flow would come across the surface. And the question is then, where do we take our offtake? Where do we put our offtake? Because it doesn't look like we've got any options at all. So what we would do is we'd think, well, what can we do? The same inflow behaves differently depending on how stratification has gone. Then we need to make sure that we're getting our stratification right, because the offtake quality is very much determined by the shape of the stratification. So it underscores the importance of getting stratification right in numerical models. It's very important. So what should we do? Well, we can do any number of things. We can install a variable height offtake. And what that means is that if we had a model that had predictions of thermal stratification at a particular time, we could change the level of our offtake so that it didn't interact with an inflow which we know might be coming because it's about to rain in a day or two. We can change that level to match our stratification or avoid areas that we think will be problematic. We can also install a bubble plume diffuser, and all they are is a bit of pipe that can be hundreds of meters long in the bottom of these reservoirs. It's connected to an air compressor on the surface, and the air compressor pushes air down into the pipe, which has holes drilled in it, and out of those holes come bubbles, and as the bubbles rise from the bottom to the surface, they entrain dense water and they mix it as they go. And so this can be some sort of way of overcoming stratification. And as a result, we can have perhaps less interaction between our inflow and our offtake, which is what we want to do. So we did have an animation here, which again, I'm afraid is not working. However, what we do see is much greater
Michael,
dilution.
I could play that video just really quickly for you if you like.
Please do. That'd be great.
No
Thank
worries.
you. Yeah.
Let me just share my screen. One moment.
Yeah, thanks.
Sorry, not that screen. This one here. All right.
There we go.
That's
okay.
all right. Yep.
Yeah, this one. Yeah, that'd be great.
I'll push
Thanks.
play. No worries.
Thanks. Okay, so here comes the inflow. Thanks, Joel. On the left pane, it's an underflow. The middle pane is a midflow. The right-hand pane is an overflow. So where that offtake should be, well, it really depends on where this inflow comes in. We want to avoid these high concentrations or browns. We want to keep it around the blues. So Joel, if we perhaps can go to the next slide and then through the next animation. Yep, no, the next animation's fine. Yep, one more slide. Thank you. If you can play this one now, we have a bubble plume installed on the right-hand side for the case of the underflow. So we see the same underflow as before, but on this side we have a bubble plume that's mixing everything vertically. And instead of having this plug flow here from the underflow with high concentrations of potentially bad stuff, we have a well-mixed water column with lower concentrations of this inflow pollutant. So where do we put the offtake? Well, it depends on what sort of stratification devices we might have in our reservoir. So again, it just underscores the need to have a model that's predicting the thermal stratification correctly. Because if we don't do that, we won't get the correct interaction of inflows with our receiving waters. So Joel, perhaps just the last slide, please. And that's it, we finished there. Thank you. So what have we learned? We've learned that climate, mixing, oxygen, nutrients, and phytoplankton are the most important things. And if we're going to model these systems, we have to get the thermal stratification right. It can be done. There's no problems in doing it, but we have to get it right. Otherwise, we have no chance at all in getting the right dynamics in our reservoirs and therefore the right water quality responses. And that's all I had, Trevor and Joel.
Michael, absolutely wonderful. And yeah, thanks so much, Joel. Just wanted to give a shout out to the Australian Water School staff working in the background to make all these things work. And Joel, you get onto that. Oh, I can't believe what graphics do in such complex systems as these things. But immediately to an uninitiated, I'm initiated, but I'm not into modelling, but understand it, just to see how that upper, middle and lower levels of water stratification happen and where to take the water from. I'm carrying on. I won't say anymore because I want to hand over to this.
It's a big issue we need to be on top of. Yeah.
Oh, yeah.
And trust our models to tell us the right thing. Yeah.
Yeah. Coming up with graphics, at least tell us what the problems are going to be so we can get to them. Come on board, Louise and Emma. Lovely to have you back again. And thank you for being with us all the way through. I see the questions going through, tumbling over each other. And there's 8 up there right now that we could address. I'm going to hand right over to Louise now to pick out the eyes out of this. Right over to you, Louise. Thanks, Trevor.
Thanks very much, Trevor. There are there've actually been 15 questions answered, and the questions keep coming through.
Great.
There's still 10 that are open. So the biggest challenge, Michael, is going to be which ones that we can answer in the next 5 to 10 minutes.
Your call, Louise. Pick some.
There's a whole series of questions specifically related to your example there, which was an amazing example and covered such a wide range of all the different tricks and tips and tricks in lake modelling.
Traps, yeah.
Traps as well. So tips, tricks and traps. But I think rather than jump into the questions about the phytoplankton, the turbulent scheme and all those sorts of things, I'm actually going to open with a really interesting question that was provided by Sean Venister, because he was asking, I know you were talking more about the deeper lakes in this, but he was asking more about, there were quite a few questions about how does that then translate to the shallow lakes?
Right.
And specifically wetlands and constructed wetlands.
Yep.
So we answered the quick, short answer to say, yep, we can use the same modelling process in the shallow. But specifically, we're talking about the feedback between the macrophytes in the plants and how that then comes back. So you could sort of give the longer a response to that question.
Yeah, thanks for the question, Sean and others. Great to hear from you, Sean. Definitely what we've talked about today applies to shallower systems such as wetlands, constructed wetlands and urban lakes. The difference there perhaps is if our lakes are wetlands are perhaps not as deep as say 3 to 4 meters as a general rule of thumb. We're unlikely to get substantial thermal stratification in those systems, but that does depend on water clarity as well. So if we have very turbid wetlands that are doing a lot of great water quality treatment, or turbid urban lakes, we may get some stratification in 1 or 2 meters of water, but generally think of 3 or 4 as a bit of a rule of thumb for that mixed or not mixed situation. In terms of the macrophytes, that's an excellent question, because what we're doing at the moment is working with the University of Western Australia to implement algorithms in our model that do a couple of things. The first is account for the impact of macrophytes on drag in flows. So in systems where we have macrophytes growing in river systems, they can slow down flows, and simulating those dynamically is something we're working on with the University of Western Australia. So 2 things: we can grow macrophytes in the water quality model, then we can have that growth feed back into the drag applied to the water by those macrophytes. And then the third stage, which we'll get to a bit more in the future, is, well, if those macrophytes detach and move downstream, they stop providing drag to the flow, but they also provide a source of nutrients that's potentially bad elsewhere. So that whole interconnectivity between the hydrodynamics and the water quality and macrophyte growth is something we're looking at right now. And I would say that applications to wetlands is exactly where we'd be thinking those sorts of things would be applied, because we know that obviously macrophytes grow in constructed wetlands because that's what they're supposed to do, to take up nutrients. That's exactly where we're heading with this, Sean. So thanks for the question. Great question.
Thanks a lot, Michael. So the other questions are more specifically about your example. So there were sort of 3 questions. One is a question is about the temperature at the beginning. At the end of autumn was 20 degrees, but the start is only 10 degrees. So sort of explaining that sort of build up in temperature. Then there were questions related to the choice of functional phytoplankton versus species, and then it was also about the turbulence closure and the application there. So just a few specific to your example.
Yeah, and like we said, a very quick survey of how lakes operate is something we need to do in this session, and there are many complexities we could dive into. Some of those are included in what phytoplankton species did we simulate, and what were its properties in terms of its light properties, or its photo inhibition properties, or its nutrient uptake limitation functions. All these sorts of things we could look at to suit different species. I just parameterize this species as a reasonably generic species we might see in a reservoir. I didn't say it was particularly toxic or not. It was just one that responded to light and nutrient uptake. I didn't simulate internal nutrients in this case. I just simulated the uptake of external nutrients for this phytoplankton species. And obviously I had a light limitation in there as well, so that when they got to depth, they died. I had moderate growth rates, I think about 1.1 per day, and respiration rates of a low 0.1, 0.2. So I was trying to make a point in my simulations and examples, but I do hope I had a reasonably representative phytoplankton species in there. The turbulence closure scheme, the K epsilon scheme we talked about, we use that scheme more often than not. The point I was making though is that we shouldn't just use it and get on with life. We should be thinking about what it's doing and how it's doing it, and whether in a particular setting there are other turbulent closure schemes that might do a better job for us. Horses for courses. And so certainly, because there's so many out there, we need to be really careful about which ones we choose. But there are many to choose from, and they're interchangeable. So it's something we have, rather than being a bad thing, it's a good thing we have at our disposal so many different schemes we can choose from to suit the systems we might be looking at.
Thanks, Michael. The question was what and where, how would you find out which scheme to use? What would you measure to sort of make that choice?
It's all about calibration. It really is all about calibration. And like I said, we shouldn't be doing any sort of reservoir modelling without calibration data. that applies elsewhere to other modelling as well, but particularly for reservoirs because they're so sensitive to these changes in climatology or mixing schemes or horizontal discretization. We really need to be saying we've elected to use this scheme for these reasons, and look, it does a pretty good job of reproducing temperature stratification. You might want to do some sensitivity analyses by saying, how about we use this other scheme and see what happens in our particular system, but we're using this scheme for these reasons, and it does a good job because we have compared it with data. And that's what we have to do. As practitioners, we have to do that. We cannot get away with not doing that, particularly in systems that are so sensitive.
Thanks a lot, Michael, because there were a lot of questions in the chat about measurements and how frequent those measurements would be. We did try our best to answer as many as they could, but it did really have a flood of questions towards the end. So the other question that we have here, which is quite a popular question, and it's something that I missed because we were busy answering the questions. It's about the fact that the temperature in autumn, at the end of autumn, was 20 degrees. But the start of the simulation was only 10 degrees.
Yep.
So it's more of a comment there.
Yeah. So I gave the model initial conditions of 10 degrees from top to bottom, and it's well mixed because we know lakes are well mixed in winter. And so I just gave it a typical winter temperature, and I let the radiation and the climatology spin the model up as time went by. So the increase in temperature you saw was a result of the climatology being placed or forced onto the model. So that warm up, that gradual spin up to a state of stratification is something we always let these models do themselves. We'd never start a model with a stratification as initial condition because we're telling the model what to do. We always let it spin up from something that's unstratified, which is why I chose that temperature. And as expected, the climatology moving from autumn into the sort of spring, summer times, it increases. And that's because of the solar radiation, more or less, and the air temperatures that increase over those times. So, yep.
Thanks a lot, Michael. And then another one that's been jumping up a bit was the let's jump back down again. We've got the wind. It's gone out because it's been answered. I'm sorry, I was ready for that one. Right. So we'll go for that. So the answer you've already sort of answered, the question you've already answered is the phytoplankton species, and you said
just a generic
one. So then we've got a very good question here in terms of, yes, this one we sort of sat there and we thought would be a really good one to answer live, because your presentation was all about lakes. But the question is, how does that then also relate to a coastal environment? Yes, it's got more complexity there, but what are the commonalities?
Yeah, certainly in terms of simulation of water quality, in estuarine systems and riverine systems and shallow lakes, perhaps coastal fringing lakes, we'd expect to see stratification. We expect to see consumption of oxygen in the sediments and release of nutrients in sediments. In the coastal ocean, if it was predominantly sandy, we would not expect to see significant uptake of oxygen from those sands because they're largely lacking in organic matter, and it's the organic matter breakdown that consumes oxygen and releases nutrients. So in those settings, we expect something different in the sediment properties. We'd also expect the phytoplankton species to be very different because it's a saltwater environment. And so freshwater phytoplankton species are typically phosphorus limited, which means they've got plenty of nutrient, but plenty of nitrogen, but they always need more phosphorus. It's the reverse often in coastal salt environments. There's often plenty of phosphorus, but not enough nitrogen. So they're very different algal species, and they have different access to nutrients supplied from different locations. Nutrients would more likely come from catchment runoff into the coastal ocean than from sediment release. So the similarities would be we'd still simulate phytoplankton, we'd still simulate oxygen, we'd still simulate mixing. We'd have to be making sure we got all those processes right, but we'd probably use different parameterizations for our phytoplankton and our bed dynamics. And we'd probably not pay as much attention to thermal stratification. We'd pay more attention to salt stratification, because we could have the situation where we had fresh water coming off the land onto the ocean and sliding across the top. And we have a different sort of stratification there generated by salt, not by heat. And we have to make sure we got that right. And there's a whole other series of processes that go with getting that right.
That's a very concise response to quite a complex question. And because of that, I'd like to finish, if possible. I know I've gone a little bit over time, but it is another very complicated question. And if you can give a succinct response, would be wonderful. The question is, given that modelling has a fair amount of variability, uncertainty, so we know models are all wrong, but some can be useful, they're representative of what's really happening in nature, but it is just that, a representation. So wouldn't it be better to focus our resources on measurements? And the question is about adjusting offtakes, and this would be in a reservoir situation, but I think this question is very generic about every lake management process. Do we invest our money into taking more accurate measurements or into the modelling side?
I'm going to sit on the fence, and I'm going to say it's not either or. It's most certainly not a situation where we say, oh, it's only modelling or it's only measurement. They very much complement each other. We should never do modelling without measurements to back it up. And we should always use modelling to inform where we go and make measurements, and what measurements we make and how we make them and how frequently. So they go together. And I think if we are interested in managing our reservoirs responsibly and being careful about where we make our offtakes, withdrawals from, we need to be doing both. And they need to be talking to each other to give us that overall managerial picture, and not investing all our eggs in one of those baskets, because I don't think they're mutually exclusive and shouldn't be.
That's fantastic. And I've seen you come back to join us, Trevor. I just, before you finish up, I just wanted to say one last question in the Q&A, but it's actually not a question, it's just a thank you. And good. Despite the technical difficulties, that was one of the clearest explanations of reservoir water quality modelling that I've been lucky enough to sit through. So thank you very much.
Yeah.
Thank you.
Yeah,
thank you.
Absolutely well said, Louise. Yeah, it was fantastic. And that last question particularly, as a non-model, I'd look at the water industry and go, for goodness sake, just get a bigger computer. You know what I mean? Then you won't have to do modelling solutions. But you know, there's ignorance speaking. They'd probably need a computer the size of the Earth to model all of the Earth's complications. Yeah, that's all right. Look, thanks so much, and thanks Emma and Louise. Michael, it's been absolutely wonderful.
Pleasure.
These are great events. I was just talking to my son before we started. He's an IT specialist and a master's in IT, and he just loves the fact that we're doing this. So do I. No, it's just a fantastic way to go. Here we go. On-demand courses, webinars, and live courses on your screen there. You won't have anything to miss here. You could pick on. This is the way to keep your learning skills up and to take control of your learning, as we were saying on the Australian Water School. It's so easy, and not getting on planes, not booking hotels, just get online, talk to the experts straight up. Well, that's my big plug for the upcoming courses. But there was one here that Joel, you picked out. Coastal water quality. Yep, this is your next webinar, Michael. Yep.
It's certainly our team's next webinar. Yeah.
Teams. Right.
Yeah, in May next year. So we're talking about what Louise meant that last question was about, differences between the coast and the lakes.
Yeah, no, thank you, thanks Joel for putting that up there. That's terrific. Draws everyone's attention to be along to that. That'd be terrific. Well, look, I think we'll wrap up here. With a lot more you could discuss. There's 16 questions there. We've got the experts on board. Why don't we go all day? Well, it's not going to happen. It's going to happen.
Hungry, Trevor. Hungry.
Hungry. Lunchtime here. Probably not lunchtime in Buena Vista or wherever people are calling in from. Ghana. Thank you everybody for joining us today. It's been absolutely wonderful. Without you joining us, would never be so interesting. Thanks to Michael, Louise and Emma, and to Joel for your background work there and your colleagues in the Australian Water School. I'm Trevor Pillar signing off here for one great webinar. Hope to see you all again, and thank you for joining us. Bye for now.
Thanks all.
Thanks for watching. Subscribe by clicking the link below and click on the notification bell to stay up to date with new releases. For the latest in significant, innovative and critical advances in water science, technology and management, subscribe now. To build your skills, enhance your technical knowledge and learn from leading experts in water, visit theaustralianwaterschool.com.au and discover our online training courses, both live and on demand.